Question 30e. A solid is made up of a sphere sitting partially inside a cone. The sphere, center O, has a radius of 4 centimeters and sits 2 centimeters inside the cone. The solid has a total height of 15 centimeters. The solid and its cross-section are shown. What is the volume of the cone correct to the nearest cubic centimeter? So we're only after the shaded region. So here's the cross-section there. Well, first thing we might do is we might write down the volume of the cone. And the cone is a special type of pyramid, which means that it's going to be 1/3 AH, okay, which is equal to 1/3 multiplied by the base area of the cone, which is going to be circular. Okay, so that's going to be pi r squared multiplied by the height of the cone, which is h. So we really need to find two things. We need the r, the radius of the cone, and we also need the h, the height of the cone. So I think we can find the height of the cone easily enough. What we might do is we might just draw a radius here from the center of the sphere O, okay, and it's going to be equal to the radius anywhere else. Okay, that's actually one of the characteristics of a radius or radii, that the distance from O to anywhere on the circumference of the circle is going to be identical. So there's 4 centimeters. Okay. Now this one's going to be 2 centimeters here. That's given. So from O to the horizontal dotted line, this one's also going to be 2 centimeters because 2 plus 2 gives us 4, which is also a radius. Now we can work out the height of the cone. So that's an easy mark to get. Okay. So might actually write it as height of cone just to make it a little bit clearer. Okay. Rather than just writing h. So height of cone, h, okay, is equal to 15 minus, okay, so that's minus 4 minus 2. Okay, so it's going to be 15 minus 4 minus 2, and that then gives us the remainder. Okay, so I might actually just draw that arrow there so you can see what I'm doing. That's going to be equal to 9 centimeters. Okay, so we have this worked out now. Now we need the radius. Okay, so from this point, okay, so from this point here to this point there. Okay, and notice that we have a right angle triangle. Right angle triangle, we have a hypotenuse, we have one of the short sides, but the other short side is the one that we need, which is the radius of the cone itself. Okay, so this is the r that we need to find. Okay, so the radius of the cone, okay, which is r, okay, is equal to, now, it's in fact Pythagoras Theorem, where we're trying to find one of the shorter sides. So we have the hypotenuse here, which is 4 centimeters, and we subtract the square of the other short side, which is 2 centimeters, all squared obviously. So hypotenuse squared minus 2 squared, so that refers to the hypotenuse in this short side here. Okay. Okay, and that's equal to 16 minus 4, okay, which is equal to square root of 12, or if you've evaluated it directly, okay, so you could have just typed it in directly here, so 4 squared minus 2 squared, and you get 3.4641. I might just write a few decimal places there. Okay, 3.4641011615. It's probably a good idea to maintain accuracy right up until the very end, and then just round it correct to the nearest cubic centimeter. Now that we have the radius of the cone, so we have our r. Okay, so volume of the cone is equal to 1/3 multiplied by pi multiplied by r squared. Okay, so that's going to be 3.4641011615 all squared multiplied by the height of the cone, and we've worked that out to be 9 centimeters. Okay, and evaluating all of that. Okay, so 1/3, okay, multiplied by pi, multiplied by, now I can sort of save a bit of time here, that was the previous answer that was on my calculator screen. So we're going to square that, and then multiplied by 9. And we get 113.09733 ... So probably gone a little bit beyond there. Okay, and then we can just round to the nearest cubic centimetre anyway, so that's going to be 113 cubic centimetres, correct to the nearest cubic centimetre.